Okay, so this is the next well video. This is a whole series of videos that are kind of tied in together. So this is part 284C3m1b7a2, line 22f1fa19c3m1b7a2, laser mixing electron-hole collision waves 5G Wow Seti. So there's the alien radio signal there. And November 23rd was when I was working on the research. Today's the 25th of November, 2012. So I'm going to Google the keyword laser mixing from the previous video, which was line 22f1fa19c3m1b7a1, harmonic microwave transponder laser mixing 5G Wow Seti. So the laser mixing generates multifrequency light from Ashley.Paddock. This is a quote from a blog. Santa Barbara, California. A groundbreaking laser mixing technique can manipulate electron-hole collisions to create many frequencies of light simultaneously. This mechanism for ultra-fast light modulation has potential applications in high-speed optical communications. Researchers at the University of California use a free electron laser aimed at gallium arsenide nanostructure semiconductor to create a quasi-particle called an exciton, a bound electric hole pair in the material. Excitons occur when a semiconductor absorbs a photon. The energy excess excites an electron, causing it to jump into another energy level and to leave behind a positively charged hole in the energy level it left. The electron and hole are bound because of their mutual attraction. So this is Benjamin Zaks on the left and Mark Sherwin on the right, courtesy of UCSB. And quote from the blog, normally the exciton would have a smaller energy than the original electron and hole, but the researchers used a second laser with a lower frequency to smash the electron back into the hole with a greater energy than with which it left. As a result, the electron-hole recombination emits photons at different frequencies than those it absorbed. So that's from www.photonics.com. Okay. Here's the artist's rendition of electron-hole recollision. Near-infrared amber rods, the terahertz, are the yellow cones, and radiation interact with the semiconductor quantum wells, which are the tiles. The near-IR radiation creates excitons, green tiles, consisting of a negative electron and a positive hole. Dark blue tile at center of green tiles bound in an atom-like state. Intense terahertz fields first pull the electrons, white tiles, away from the hole and then push them back toward it. Electron paths represented by blue ellipses. Electrons periodically recollide with holes, creating periodic flashes of light, white disks between amber rods that are emitted and detected as sidebands, courtesy of Peter Allen, UCSB. Source of the photo is photonics.com. Quote from the blog is, the cable is a bundle of fiber optics, and you're sending a beam with a wavelength that's approximately 1.5 microns down the line. But within the beam, there are a lot of frequencies separated by small gaps like a fine-tooth comb. Information going one way moves on one frequency, and information going another way uses another frequency. You want to have a lot of frequencies available not too far from one another. Because the laser currently used is the size of a building, the researchers are forced to come up with a more practical way to implement these findings. One solution is to use a transistor that modulates in the near-infrared to produce a strong terahertz field akin to those of the free electron laser. So here's all the little parts that go with it. Apparatus used for electron-hole recollision experiments, large flat and curved mirrors guide and focus terahertz radiation emitted in a different room by one of the UCSB free electron lasers. Through a round cryostat window on the sample, not visible. Smaller flat mirrors guide near-infrared radiation from the left through a small hole barely visible at the center of the curved mirror surface through a round cryostat window in the sample, not visible. Near-IR laser and sidebands caused by recollisions in the sample exit through a second cryostat window hidden are reflected by the small round mirror on the right and directed to a spectrometer, not visible, courtesy of Ellison McElwee, UCSB. It's photonauts.com. Okay. 23 of November, my thoughts. I was very interested to read the large, flat, and curved mirrors are used in this experiment. The mirrors formula in the alien well data use Obsidian and different types of spheres. So Google the keyword terahertz radiation waves in the next video. Thanks for watching.